So this afternoon I went to Vetco, which is a electronics surplus type place where you can buy wire, you can buy components, you can buy junk, to pick up some equipment for my lab that I needed. I got this anti-static mat. It's used, but I only paid $12 for it, which is a pretty good deal. So now I have a nice anti-static mat. But while I was there, I noticed this thing in their surplus section. See if you can see it. This is an ECG simulator. So I guess you plug in your ECG machine, and you can simulate various aspects of what a patient's heart would do. And of course, I couldn't resist picking this up, especially since I only paid $9.95 for it. These connectors here, plus this nice rotary switch, and this pot up here that also clicks, and the enclosure are definitely worth $10. So I'm going to do a little teardown of this thing. I have no idea what to expect. I tried finding some documentation online, but I got nothing. There's not even a part number on this thing, at least not that I can see. There's a patent number, there's a serial number, and a calibration sticker. And interestingly, this calibration sticker says calibration not required, but this one says calibration. Go figure. So anyways, there's an LED there that's not doing anything when I turn this to not off. So I'm guessing the battery's dead, but since it says 9-volt battery, I might want to throw this one in here and see if I can't get something out of it. See how to get this thing open. I don't see any screws. I bet they're under these little feet. Oh, and before I forget, Vetco is an awesome place. I think I already mentioned that. So I'm in the Seattle area, and if you live in the Seattle area as well, you should definitely go visit them, because they've got everything you need. They even have Arduino products. They have various sensors. They have, here's a dot matrix LCD with EL backlight for $13. Not bad. They've got tools, all sorts of stuff, and they're expanding, and they're open 7 days a week, so you should definitely go see them. Of course, I don't work for them, but I think they're awesome anyways. Now before I start tearing this apart, let's take a look at it at least. So it's by Valonix, however you want to say it. You've got your various connections for those snap connectors that they use for connecting to ECG machines. You've got your level adjust, and I guess a calibrated 1 millivolt if you push in. I'm not sure exactly how that works. What I'm assuming is a power LED, calibration holes. There's 2 little trim pots down there, a broken cal sticker, and you've got a whole bunch of banana jacks. These seem to correspond to these, and then you've got a whole bunch of other connections which match in color to this one, V. Not sure exactly what it stands for. Definitely not a doctor. Maybe ventricular or something or other? Ventricle? I have no idea. I'm just going to sound like an idiot. So, yeah, on the back there's nothing of interest, on the side there's nothing of interest, and on either end there's nothing of interest. Although I do notice that I think someone's tried to get in here, because there's the telltale screwdriver pry marks. Now something that I find quite interesting is that there's no way to get to the battery that I can see without opening this. So I don't know, is it designed to be a limited use thing, so when the battery runs out it's done? That seems kind of strange. Oh, and I forgot about this. This is just I guess the heart rate selector and off. So you can go from freaking out to kind of freaking out all the way to dead. So I've already looked under here. There's no screw holes, so I'm hoping that I don't have to peel this thing back. It'd be a shame, but I can't feel anything that would suggest screw, although this thing is pretty thick, this little piece of adhesive. So I guess I'll peel back the corners and see what I find. And of course this thing is kind of old, so the thing has become brittle, so I tried to peel it back just a little bit and it just broke. So I don't want to shatter and destroy this whole thing, because if all else fails, I want to just display this as kind of a curiosity, and I want to have the sticker of, you know, random dude on it. So I think I might have to use the old heated razor blade trick to kind of melt the glue underneath and try to get this off without breaking it. Then I can maybe reapply it later with, I don't know, some sort of other adhesive. There's nothing under that corner. What a bummer. Well, as usual, I complicate things. Turns out that the pry marks were really how you get in there. It's just snaps together. Alright, let's see what we're entrusting our EKG developers to. Oh, it's upside down. Interesting. Definitely got a budget PCB in there. It doesn't even have a solder mask or silk screen, at least on this side. It's all tinned copper. Battery doesn't seem to have leaked everywhere. That's good. I'm going to just try real quick replacing this battery and turning the switch. See what happens. I see a little beating heart. Maybe you can't see it. Let me turn off the light. Turn off the other light. This thing is really dim. Yeah. 60 beats per second. That sounds about right. 180. Guy's really freaking out because we're about to turn him off. Ah. Alright. Cool, so it seems like it works. Of course, let's hook it up to that. Unfortunately, the scope isn't picking anything up at all. I have it on its smallest, or its most sensitive setting. Oops. Faceplate. But I can't get it to see anything, so I'm going to have to open this up a bit further and see what makes this thing tick. Maybe we can reverse engineer it. So to remove this board, it looks like I only have to unscrew these 4 nuts here that correspond to, actually there's 5, sorry, that correspond to those snap points, and we should be able to lift this off and see what's going on. This thing has actually pretty nice construction. Looks like it's all hand soldered in here. Also these. This very nice rotary switch, and this very nice clickable pot here. This is not a 10-turn pot, it's a regular 270-ish turn pot, but anyways, let's get these nuts off. Well, here's a closer look at its guts from the other side. It looks like pretty classic construction, no surprise. So it looks like I can just pull off these connectors, and we can take a more leisurely look at the construction of it, and hopefully reverse engineer. Well, this is certainly interesting. So this rainbow cable goes into what looks to be a dip adapter here. Looks like these 2 pins at the end are assembled. They're shorter than the rest. Actually, this one down here is as well. See, it's a different length. But I guess this must have worked at some point. Anyways, I'll put this aside. And we'll take a look at here. So, as I was looking at this, see our first hack. There is a small capacitor soldered onto the legs of another capacitor. Nice. Apart from that, it doesn't look like there's any other hack. I guess for medical equipment, that sort of thing wouldn't be allowed, but I guess this isn't keeping anyone alive, so who knows. Now the second thing that strikes my eye is how many unpopulated footprints there are. There's a whole bunch of look like dip and just discrete part footprints that aren't populated. And I also notice that where was it? This thing is revision M. So I was kind of surprised they didn't fix this by the time revision M came around. I guess it was a new problem brought about by some, I don't know, revision L. Maybe that introduced a subtle problem there and they had to go in and fix it. Alright, so let's start looking at devices. This thing is an MC14584. This is just a Schmidt trigger. This is an MC14020, which is just a counter. This one is an MC14566, which is a time-based generator. It contains various. It contains a divide by 10 and a divide by 5 or a divide by 6 counter, so that you can use this to get 1 Hertz out from either European by using the divide by 5 after they divide by 10, or US line frequency. However, it also contains an internal oscillator, so I guess that's what they're using here, because this thing isn't plugged into the mains. This thing down here is a CD4017 counter. Same thing here, and this is an LM324 quad op amp. This device here looks to be an oscillator of some kind, maybe a crystal or otherwise. And that leaves these green things. There's 3 of them. They're all different, or at least marked differently. This one is marked REN V2A CTS 8111. This is REN V3 CTS 8113. And this one's REN V4 CTS 8127. I don't know what these are. They might be resistor arrays, or they could be custom chips. I am not really sure. That might make reverse engineering this a bit of a problem. Oh, and almost forgot these little guys. This is a 78L05A 5-volt voltage regulator, and these two are just 2N3904 NPN transistors. Actually, while trying to reverse engineer this, I did some probing around, and at least that thing looks to be a precision resistor array. So I'll just finish reverse engineering at least the output part of this, and we can see what's going on. Alright, so I've been staring at this for a while, and I get the basic gist of it. I'm not going to draw it out, but these are resistor networks, precision resistor networks. I've just probed around and got the various resistance values. So I built up the main outputs, at least the very outside of the outputs, if that makes any sense. And basically they've got this resistor divider here, presumably modeling what resistance the human body presents for all the points. This C is corresponds to this thing here, and then you've got RA, LA, RL, and LL, and they go in that order here, and basically they inject signal into various places in this resistor network. These aren't the exact points where they put them in. I didn't bother to trace them exactly, but that's how they kind of generate the human body analog. So this is how they do that. And of course there's more outputs, and there's just, what we're looking at here is, which one was it? It was this one, this resistor network here. Then there's this one on this side to take care of all these other outputs here that are not brought out to that little top panel. And as for how they actually generate these signals, I'm pretty sure that what you're looking at here is a very special version of a digital to analog converter kind of like an R2R ladder. Yeah, now here's an R2R ladder schematic on Wikipedia, and basically how this works is you have your digital outputs connected to these resistors going vertically here, and then you've got this resistor divider along here, and basically depending on which digital inputs are turned on up top there, you get a different voltage out. So that's a basic implementation of a digital to analog converter. You can read up about it on Wikipedia. Just look for R2R ladder or resistor ladder for the more general article. But anyways, the R2R ladder is called R2R because it uses values of some resistance and then resistors of double that resistance, so say 10 ohms and 20 ohms. What I think is going on here is that this resistor pack here has very specific values to correspond to the various phases of a heartbeat. So it bounces up and down and has a very characteristic shape and very characteristic peaks. I think they've just optimized the specific values of their resistor ladder and have it hooked up directly to the counter, like up here. This is the counter, so that as the counter counts up, it activates different parts of this resistor divider and then it creates a waveform. I've looked at how this LM324 op amp is wired, and it's just basically a bunch of buffers with no gain, or a gain of 1, which then feeds up into this area to this thing here. So it's a very nice implementation. I like it. It's very simple. There's not much to it, and I don't think it's gonna break. So I think I'm just probing this thing wrong. I guess I'll try again, but that's the basic operation. You've got your counter, drives some sort of ladder, so digital to analog converter that's built in such a way that it'll basically generate a heartbeat kind of by itself. You don't need much intelligence. Some buffers, some resistor dividers. I guess this is what Mythbusters would call your human analog. And yeah, that's it. Oh, and the time base here to generate your, I guess, the various phases of the heartbeat, and timings for that. Clocking your counter here, and there you go. You have a heartbeat simulator. Whoever bought this probably spent money out their nose, but there's not much to it. These days it'd probably be even cheaper, because you just have a microcontroller, control a real digital to analog converter, so you could simulate probably all sorts of things, heart conditions, all sorts of interesting variations. Anyways, I'm gonna start probing this again and see if I can get any sort of signal out of it. If not, then well, I'll end this video here. Well, the stupid LED fell off. There's been a lot of stress on it, I guess, but I soldered that back on, no problem. Anyways, just thought I'd tell you that. Well, I'm afraid the most heartbeat-like thing I could find was this thing, but it's more of a crappy square wave, really. I push it to storage mode. That's what it looks like. Maybe that's a better view. And turn down the brightness. There. Not very exciting. And that's not even off of one of the connections. It's just some random point I found that looks good on the board. The output of one of the buffers on the LM324. But yeah. Oh well. That's that. I think I'm sick of this. But in case you're wondering, this is where all the connections go on the human body. I keep thinking of Deus Ex Human Revolution. Go to your limb leads. Especially when they start talking about, augmented limb leads. In case you have a spare arm or something like that? No, I guess not. Anyways, the V leads go over here. Anyways, thanks for watching. I hope that was at least a little interesting. Too bad it doesn't work. I guess this is why it's in the surplus section, because it looks like it's broken to me, unless I'm missing something pretty obvious. But I can get no signal at all down here, and that's where all these things are connected. And this is all just one big resistor array, so I should be able to get at least something, but I can't even get any signal off of the points where the signal is injected. So I think that's that. I'm gonna go wash my hands because I'm sure this is leaded solder. Don't want to get too much of that on my hands and then on this peach that I'm about to eat. But anyways, thanks for watching.